If a system is represented by a transfer function, how do we represent the system in controllable canonical form? But for a very specific case where the numerator order m is 3 in this case, and denominator order of the polynomial is 3, where m is equal to n, a special case. For this one, we will see how to represent it in controllable canonical form. We can write this y of s by u of s as y of s over x1 of s times x1 of s over u of s. And I'm going to split this transfer function into two parts, which is first with numerator divided by 1 times 1 over s cube plus 9s square plus 23s plus 15. Now we can say this y of s is associated with this expression over here, and whereas x1 of s over u of s is associated with this expression. Now we will write this into two equations. The first one, y of s over x1 of s with numerator. Y of s can be written as x1 times s cube plus 12s square plus 44s plus 48. I'm going to rewrite this expression. Y of s is equal to s cube times x1 plus 12s square times x1 plus 44s times x1 plus 48 times x1. I'll rewrite this into time domain form, which is y is equal to x1 triple dot, which means in Laplace domain, if we say s cube times a variable, in time domain it is d cube over dt cube times x1 of t. This in short form we are representing it as x1 triple dot. And similarly, if we have s square times x1, we write it as x1 double dot, representing 2 times differentiation in time domain. So let me write it here, 12 times x1 double dot. So let me write it here, d square over dt square of x1 is x1 double dot, and similarly d by dt of x1 is x1 dot. Here 44 x1 dot plus 48 x1. Now we are going to define other state variables as x2 is equal to x1 dot and another state variable x3 as x2 dot. But I'm not going to define a variable called x4 because here we have x1, x2, x3, 3 state variables defined already, and the order of the system is 3. So we will have only 3 state variables. Let me rewrite this expression in terms of x1, x2, x3. So y is equal to, I can write x1 triple dot as x3 dot. So we know we don't have x4, so the only thing we can have is x3 dot plus 12 x3, because x2 dot is x3, which is nothing but x1 double dot. x1 double dot is x3 plus 44 x2 plus 48 x1. So this is the output expression that we have here. Now let us go to the second expression that we have, which is x1 of s over u of s in terms of denominator polynomial. U of s is equal to s cube times x1 plus 9s squared times x1 plus 23s times x1 plus 15 x1. Now we can rewrite this as, in terms of time domain, x1 triple dot plus 9 x1 double dot, just like in the previous case, 23 x1 dot plus 15 x1, u equals to. Now we can write in terms of the definitions we did, x1 dot is x2, x2 dot is x3. We can say this is x3 dot plus 9 x3 plus 23 x2 plus 15 x1. Now we have 4 expressions, 1, 2, 3, and the fourth one. We need to express these 4 equations in terms of vectors. X dot is equal to matrix A times x plus b times u, and y output expression c times x plus d times u. So in that case, x dot should be depending on x variables and the input. So if you see here, x variables are depending on u. Y should be depending only on x and u. But in this case, we have y depending on a derivative of the variable as such. So what we should do is find the x3 dot from here and substitute it in this case. So I'm going to substitute x3 dot from this expression. So first of all, let me write what is x3 dot, which is equal to u minus 15x1 minus 23x2 minus 9x3. So let me substitute that into this x3 dot. Then y becomes u minus 15x1 minus 23x2 minus 9x3 plus 12x3 plus 44x2 plus 48x1. So I can rewrite this y as u minus x1, we have 48 plus 48x1 minus 15x1. We'll have plus 33x1, and for x2 we have plus 44 and minus 23. It will become plus 21x2. For x3 we have 9x3 minus plus 12x3. So we can say it is plus x3. Now we have four expressions. One is x1 dot equals to x2, x2 dot equals to x3, and the expression for x3 dot, and the expression for the output. We'll use all these four expressions to find the system equations in this form. We have these four equations. We need to represent them in terms of x1 dot, x2 dot, x3 dot, a vector, which will be equal to a 3 by 3 matrix, which we call system matrix A, which will be 3 by 3 because the order of the system is 3, times the state vector, which is x1, x2, x3, plus a matrix again with, which is called B, 3 cross 1, 3 rows and 1 column, times u, and output y is equal to 1 cross 3, 1 row, 3 columns, times the state vector, which is x1, x2, x3, plus, if the output depends on u, we have a single value here, 1 cross 1 matrix. We call this matrix here as C, and this is D. Now let us find x1 dot in terms of x1, x2, x3 and u. We see here x1 dot depends only on x2, nothing else. So for rest of the parameters, positions, the value is 0. And only for x2 it is 1, because x1 dot can be written as 0 times x1, 1 times x2, plus 0 times x3 plus 0 times u. So we have all added together, just x1 dot is equal to x2. Similarly, for x2 we can write 0 times x1 plus 0 times x2 plus 1 times x3 plus 0 times u. So that's the expression for x2 dot. For x3 dot we have minus 15 times x1 minus 23 times x2 minus 9 times x3 plus 1 times u. So now we have the values for A and B matrix. Now let us find for C. Y depends on x1, x2, x3 and u. So in terms of x1 it is 33. Y is equal to 33 times x1 plus 21 times x2 plus 3 times x3 plus 1 times u. So this is how the state equations and output equations are written. Now let us see how to represent these equations in terms of signal flow graphs, SFGs. x1 as state variable, let me take this node as x1, and we have x1 dot, which is x2. So if I integrate that x1 dot, which we are also calling as x2, with 1 over s, the integrator transfer function, we get x1. And similarly, we have x2 dot. If we integrate x2 dot with the integrator, which is 1 over s, we get x2. Now to get x3, we have x3 dot integrated, we get x3. Now we have all the three integrators. Three integrators represent the order of the system, 3. So number of integrators you see in a signal flow graph represents the order of the system as well. So now we have x3 dot expression. We can say x3 dot is equal to minus 15 times x1 minus 23 times x2 minus 9 times x3, and it also depends on u, so 1 times u. This is, let's say, u. Now let us see the output expression, the y. Y depends on x1, x2, x3 and u. So x1 is here, so let me say this is y. So this is 33 times x1 and 21 times x2. X2 node is here, so this is 21 times x2 and 3 times x3. So another branch like this, 3 times x3 plus 1 times u. So this node is u, so I need to take one magnitude and take it over, combine with the output, so 1. So to make it look simple, I'm taking this as u times 1, both are u, and y is here. Let me take this as y with 1. This is how the signal flow graph looks for this particular transfer function we tried to find in controllable canonical form. We call this canonical form because it's a standard form to represent if the system should be controllable. And we will discuss what controllable means when we go to controllability and observability of a system.